My name is Paula Stocco. I'll share our work in safe planning under uncertainty. This work was presented at ICAPS 2024. Our motivation is to develop automated planners to solve problems where some objectives cannot be violated. In the case of multi-objective problems with safety-critical constraints, a scalarized reward function may be insufficient to guarantee these objectives are met. And these problems are represented across a variety of fields. One of our experiments uses the sizzle-developed mathematical representation for underground carbon sequestration, in which case we model spills as costs. This presentation covers short-sighted decision-making and online planning, how we can address this during search, and finally our results which empirically demonstrate a reduction in cost violations. To mathematically model our problems, we use POMDP, where MDPs are used to describe sequential decision-making problems where the reward and dynamic models are stochastic. We assume the state of the world is not known, so we use observations to maintain a belief, and we incorporate separate costs and constraint budgets. We want our automatic planner to return a policy that, from our initial belief, will maximize cumulative reward subject to satisfying the hard constraint budget. Constraint Tiger is a toy problem we can use to review how Monte Carlo tree search can be used to solve CPOMDPs, to review when short-sighted search can occur, and to demonstrate how short-sighted search can lead to short-sighted decision-making. In this small discrete problem, we're rewarded for avoiding the tiger, a negative reward for listening to localize the tiger, and finding the tiger incurs a cost. In CCPOMCP, a search tree can be built with a black box simulator, and by observing the outcomes of the simulated actions, we can estimate the value of an action. After the tree is built, we select an action expecting to maximize probable long-term accumulative reward within constraints. To find a single value to make a decision, we can write the dual for the linear program to solve our constraint optimization problem, and from that, adapt a scalarized action value. During search, we update action values, visitation numbers, and the dual variable. While we explore, we use the scalarized action value to make search decisions, and then after the tree is built, to make action decisions. CCPOMCP has a single dual variable used throughout the tree, meaning the scalarized action value at a given node used to make the decisions during simulation balances this equation with the same dual variable value, regardless of the remaining cost budget in that branch or possible future actions. Reviewing the results of tree search for constrained tiger using a single dual variable, we see in the square action nodes low exploration of the listening action, and instead search is concentrated on directly opening the door. So ultimately, shown in red, this algorithm is choosing a high-risk, high-reward action when the safer passage is possible. Our modification CCPOMCP Plus keeps belief-based lambda values such that exploration decisions during simulation are made with scalarized action values calculated with local dual variables that are based on or updated on the local remaining budget and vary with different subsequent action outcomes. With local dual variables, we can explore the high-risk but relatively safe actions after a low-reward action. And therefore, we discover this path of listening once and then opening the door. In blue, we see that CCPOMDP algorithm chooses a policy, and this halves the occurrence of cost budget violations across all our runs. With the toy problem, we demonstrated how tree search converges differently for local and global dual variables and how that affects decision making. This happens because search is controlled differently, and we'll use a simple CPOMDP with a cost limit of 1 to demonstrate this. Previous work observed a single dual variable returns pessimistic values rather than the best possible actual outcome. In the case where we have one global dual variable, if the global dual variable is less than 1, we can explore the A1 action after initial belief. However, exploration continues with the A1 action, and we backpropagate these high cost and high reward values for our A1 action estimates. In this case, we are backpropagating values that are pessimistic. By using local dual variables, we guide search with belief-based local cost constraints, meaning after our A1 selection, we select A2 and backpropagate controllable actions. In this way, search is conducted in closer to a closed loop manner. We incorporate history-dependent decision-making by updating local dual variable values based on local remaining costs. And you see that the local dual variable is a function of history. So far, we looked at small problems to demonstrate the mechanics of tree search, but our goal is to solve large problems. POMDP uses dual progressive widening and weighted belief updates to accommodate large continuous action state and observation spaces, making it applicable to more real-world problems. With this algorithm, similarly to before, we're using local dual variables instead of a single global dual variable. We demonstrate our large continuous case with the constrained light-dark problem. In this problem, an agent starts in a dark region with a low certainty of location. It will receive a reward in the green region, but moving into the red region will violate the cost constraint. The constrained agent should choose a middle-sized action to move towards the light region to localize itself without overshooting and violating the cost constraint. Using global lambda means that search after the mid-sized step proceeded with larger steps, returning unsafe costs. And in the case of this normal cost propagation, we saw that pessimistic cost values resulted in choosing overly conservative actions. So we had a very high cost estimate for the middle step and ultimately ended up choosing small steps. Using local lambda means search at different belief nodes can proceed differently, with more cautious steps occurring after larger steps. In that case, we saw that the middle step was searched a higher proportion of time and then chosen a higher proportion of time. And overall, we see a decrease in cost violations across all runs. Each local dual variable would need to converge on its own, and this approach may increase the required sum of convergence depending on how often subtrees are explored. We do note a new node's dual variable is initialized with its parent value, reducing convergence time. Constrained Monte Carlo tree search methods guided by global dual variables can be myopic, yielding excessively risky or cautious actions as a result of improper exploration. To address this, we propose local dual variables to guide safe, history-dependent action selection and optimize them using recursive dual ascent. We empirically demonstrated that our approach resulted in a decrease in simulation spent exploring unsafe or overly cautious actions, ultimately improving safe outcomes.